This is ChainMind, the decentralized AI network built for everyone. Just search ChainMind on Google, sign up, download the app, and you're in. That's it. You've joined the network. Run it on any device, phone, laptop, or server. Why ChainMind? Fully decentralized, fully yours.
When Waymo threw open the trunk of its newest robotaxi and revealed a chip that can crunch a quadrillion operations every second, most people stared at the number and thought, wow, that's fast. What they missed was the deeper story, a purpose-built compute stack that turns a moving car into a miniature supercomputer, and a blueprint that shows exactly how a network of tiny, efficient nodes could power the next generation of AI services. Everywhere. The first thing to understand is why raw compute is the beating heart of autonomous driving. A self-driving car isn't running a single algorithm. It's running a cascade of perception, prediction, planning, and control loops, each demanding sub-millisecond responses. A camera spots a pedestrian, a lidar paints a 3D map of the street, radar confirms the speed of an approaching cyclist, and then a series of neural networks fuses all that data into a coherent scene. Those networks are dominated by matrix multiplications, convolutions, and attention layers, operations that traditionally belong in the data center, where power is cheap and latency is measured in milliseconds. Put those same workloads inside a vehicle, and the constraints change dramatically. You have a strict power envelope, a limited thermal budget, constant vibration, and a non-negotiable need for deterministic latency, because a delayed brake command can mean the difference between a smooth stop and a collision. The compute platform therefore decides how many sensors you can mount, how complex your models can be, and ultimately how safely the car can navigate a crowded downtown street. Waymo's answer to those constraints is a modular compute chassis that looks more like a high-performance gaming rig than a car part. Inside the trunk sits a collection of custom ASICs, each one a dense forest of low-precision multiply-accumulate units, paired with high bandwidth memory and a dedicated networking fabric that stitches the chips together. The architecture is tensor-first, meaning every piece of silicon is optimized for the dense linear algebra that powers perception models, rather than generic integer math. This focus lets the system deliver a quadrillion operations while staying under a half-kilowatt power draw. But the design doesn't stop at raw horsepower. Waymo adds a secondary processor that handles safety-critical functions, hard real-time control loops for braking and steering that cannot tolerate the occasional jitter of a deep learning accelerator. By physically separating safety code from perception workloads, a sudden spike in neural network demand never jeopardizes the car's ability to stop on a dime. The shift from off-the-shelf GPUs to these custom ASICs is more than a branding exercise, it's a fundamental redesign of the compute trade-off space. GPUs excel at parallel workloads, but they pull a lot of power and their performance can be unpredictable when you need deterministic timing. Waymo's ASIC, by contrast, packs thousands of 2-bit and 4-bit multiply-accumulate units that have been proven, after careful quantization, to retain the accuracy needed for perception while slashing energy consumption. Low-precision arithmetic reduces the amount of data that has to be moved, and the chips-on-die high-speed SRAM keeps feature maps right next to the compute units. That eliminates costly DRAM accesses and cuts latency dramatically. Think of it like having a kitchen where every ingredient is already on the countertop instead of having to run back to the pantry for every spice. The result is a tighter, faster pipeline that can keep up with the frantic pace of a city intersection. Power and heat are the twin demons that any edge device must tame, and Waymo's engineering team turned those challenges into design drivers. The chassis runs on a 5-nanometer process, which packs more transistors into a smaller area and reduces leakage currents. Aggressive power gating shuts down portions of the chip that aren't needed at any given moment, while a liquid cooling loop snakes through the trunk, pulling heat away from the ASICs and maintaining a stable temperature envelope from desert heat to sub-zero winters. That cooling system isn't an afterthought, it's co-designed with the silicon so that temperature fluctuations don't cause timing drift in the safety processor. By keeping the compute module compact and centrally located, Waymo also shortens cable runs, reduces electromagnetic interference, and simplifies integration with the vehicle's existing power distribution. In practice, that means a sensor suite that can be placed wherever it makes sense for vision, rather than being forced into a suboptimal spot just to keep wiring short. Hardware alone would be a glorified paperweight without a software stack that knows how to wring every ounce of performance from it. Waymo runs a layered framework where low-level drivers expose a deterministic API to higher-level inference services. Those services are containerized, allowing engineers to push updates, run A/B tests, and roll back changes without rebooting the entire vehicle. At the heart of the system sits a scheduler that balances latency budgets across perception, prediction, and planning tasks. When the car approaches a complex four-way stop, the scheduler can allocate more tensor cores to the high-resolution camera feed, ensuring the model sees every pedestrian and cyclist. Once the vehicle merges onto a highway, the scheduler shifts resources toward lidar processing, which becomes more critical at higher speeds. This elasticity mirrors the resource allocation strategies of cloud AI platforms, but it happens on a single edge node, with the added pressure that any missed deadline could endanger lives. The result is a deterministic, safety-aware runtime that turns raw compute into actionable intelligence in real time. But here's the part most people get wrong. Waymo's robotaxi brain isn't a closed-off, proprietary monster that can't be replicated or shared. In fact, the very design choices they made illuminate a path for decentralized AI inference networks like ChainMind. The key insight is that ultra-high-performance inference doesn't have to live in a massive data center. It can live in a compact, low-power node that communicates with peers over a high-speed fabric. For a decentralized network, that means you can enlist thousands of such nodes, whether they're in drones, delivery robots, or personal cars, to collectively deliver the throughput required for demanding workloads. The lesson is twofold. First, hardware specialization matters. General-purpose CPUs and GPUs still have a role, but the economics of large-scale inference favor purpose-built ASICs that trade flexibility for efficiency. Second, a robust orchestration layer is essential. A token-based marketplace alone won't cut it. You need a standardized runtime that can schedule, monitor, and reallocate workloads across heterogeneous nodes, just as Waymo's scheduler does inside a single vehicle. By providing that runtime as a service, ChainMind can let developers offload heavy perception models to the network while keeping latency critical control loops on device, preserving safety while unlocking the computational power of the entire mesh. Looking ahead, there are still open challenges before a truly decentralized inference fabric can match the reliability of a Waymo fleet. Security is paramount. Each node must prove it's running authentic models and not leaking proprietary data. Trusted execution environments and zero-knowledge proofs are promising, but integrating them with high-throughput ASICs without throttling performance remains an active research area. Model portability is another hurdle. Autonomous driving models are often fine-tuned for a specific ASIC and trained on petabytes of data. To make those models usable across a heterogeneous marketplace, we'll need universal standards for quantization, compression, and hardware-agnostic graph representations. Finally, the token economics must reward not just raw compute cycles but also uptime, reliability, and compliance with safety regulations. Waymo's tightly controlled fleet demonstrates the value of guaranteeing performance. A public inference marketplace must emulate that guarantee if it hopes to attract mission-critical workloads. In the end, Waymo's robotaxi brain is more than a headline-grabbing showcase of raw flops. It is a concrete reference architecture that shows how you can pack massive AI capability into a tiny, power-constrained box, orchestrate that capability with deterministic software, and keep safety at the forefront. For ChainMind, that blueprint tells us exactly what to build: compact, tensor-optimized accelerators paired with a safety-aware runtime, all exposed through a unified API that lets any edge device plug into a global inference fabric. As autonomous vehicles, drones, and robots continue to populate our streets and skies, the demand for onboard inference will only accelerate. By learning from Waymo's design choices, and by extending them into a collaborative, token-incentivized network, we can turn a scattered collection of edge devices into a powerful, resilient AI supercomputer that serves everyone. If you're excited about the future where every autonomous machine can tap into a shared intelligence, hit the subscribe button, follow ChainMind on every platform, and join the conversation. Together we'll build the decentralized inference network that turns the promise of robotaxis into a reality for every edge device on the planet.